Today is the last day of phase diagrams. What I'm going to do is we're going to derive equations such that whoever. All right, there you go. All right, so today is if I give you the triple point, that means I give you the pressure and temperature at the triple point. What you can do is draw the remaining lines, and there you go. So that's what we're doing today. But let me back up. Last Friday, and I do have I have the videos up, or actually I have to admit I had messed up one of the links. The video, no, I have them all on YouTube. I just did that right before class. All the videos are on YouTube, including the extra hour on Friday. I went ahead and included that because I know a lot of you weren't there, but anyway, it might be very instructive. And I do have Friday's lecture, the main lecture. So we covered what's called Gibbs phase rule, and it's kind of as interesting as warm milk. What it does is it tells you, so don't forget this, I don't want you memorizing stuff, but C is number of components, and in every phase diagram you see like this is a one component phase diagram. I can tell that this is water because the way the P versus T line, slopes to the left. Okay, 2 comes from P and T. C again is one component. Doesn't have to be that way. You can have mixtures just like we were covering last week. P is number of phases. And what it does is, there's a level to this which is like childlike, which is that if you 2 plus, again, this is a one component phase diagram. Minus 1 phase, you have 2 degrees of freedom. So you draw, so that's a plane. If you have one component in 2 phases, that would be here. Let me remind myself, solid. Hopefully I'll get this right this time, gas, liquid. If you were talking about having, creating a phase diagram with 2 phases present with 1 component, you have 1 degree of freedom. And what that means, this is where I could probably put a question on the test 3. Well, that means that if you move a certain temperature, it gets hotter. Let's just say that for the heck of it, it gets hotter. Then you have no choice about what the pressure change is. It's predetermined for you. And if you don't follow the phase diagram and change the pressure by exactly a certain amount, then you will no longer have 2 phases. You'll collapse to either the gas or solid phase, how I drew it here. Okay, so that's what it means to have 1 degree of freedom, and then if you have a triple point, you have no degrees of freedom, but that's why it's a point. Okay, blinding is like again, middle school simple. But let me give you a bigger picture. It's the design principle. This is the thing that tells you how to set this up to begin with. It's just hard to see because the one component phase diagrams are very easy. So imagine I asked you, okay, dogs and cats. You can have a certain dog and cat ratio, you have a certain area of living space, and you have a certain ratio of dog food and cat food. All right, those are the parameters. What are the phases of their friends or their enemies? All right, so I want you to create a plot of dogs and cats living together as a function of those variables. Okay, and you're looking like me, like, okay, well, I bet if there's lots of room, they're friends, and if there's not lots of room, then they're enemies. Okay, yeah, I get that. But how would you really what's your first pass at that like? What would you even begin to do? Should you draw it in 2 dimensions, like I've drawn everything in 2 dimensions because of a board? Maybe you could try to draw 3 with a computer, or, you can get a little fancy or something. What do you do? How do you even begin to design this thing, right? This is what tells you how to do that. Okay, so anyway, that's the big picture. But then once you figure that out, how do you draw the lines? And that's what we're doing today. So anyway, that's all I really have to say about that. Okay, now for the lines, what you do is, since we're going to do 1 component, anything, in terms of like 2 degrees of freedom, there's really nothing to do, right? You can change temperature and pressure, and there's nothing to do because you're in a single phase. Question?
What would be the 3rd dimension?
Well, in this case, there isn't one, and this thing tells me that because it's 1 component. Okay, let's say that it was this is water. Let's say it's water and ethanol. Okay, then I would have Okay, so let's focus on the solid phase. So how would my representation of the solid phase, and I have to take this step by step, how would my representation of the solid phase change if actually this was a water and ethanol mixture? 2 plus 2 minus 1 is 3. That means that I have to add a third dimension, which would be the mole fraction of water, or ethanol would be just 1 minus that, and that's because as much as I think I control how much water or ethanol I add, I truly do, but that can be characterized by a single parameter, the mole fraction, with water being 1 minus that of ethanol. Okay, so I would have to draw another dimension, and so the area in the solid phase diagram would now become a volume. And of course, as you imagine, I need a computer to represent that. Okay, what about the boundaries? Okay, 2 plus 2 minus 2 is 2. Okay, so now I ask you this. Instead of a line, again, if I added a dimension of mole fraction, that means I'm actually doing the phase diagram of a mixture. What do the lines turn into? Planes, which, as you can imagine, or better yet, surfaces. Right? Does that kind of connect a little bit better? So I can imagine that this thing is now coming at me, and these are no longer lines; they're coming at me too, which means that they're now planes. So anyway, yeah, kind of see now. And then of course, if I add something else, or God knows what else I do, then I have to draw it in 4 dimensions, and I can't. Not even on a computer at that point. Right? So yeah, I mean, it's really quite easy. If I ask a question on the exam, if I asked a question, that would basically be it. I'm not sure about that because there really isn't much I can do with this because, again, it's kind of middle school level. If I think of something, I'll think of something clever, but it'll be easy. All right, now, again, for how do I describe the lines? The equation for lines, and that's really all we're going to do. Okay, now, we'll just we'll just make 2 phases. I got to remember how to do this. We'll just say that 2 phases have equal chemical potential. Again, remember, Greek superscript letters means phases. I brought that up a while ago. I'm not testing you on that, but that's what that is. Okay, neat thing about this. We've talked about how equilibrium chemical potentials are equal. We've done that to death. Hopefully you know. Remember when we talked about water melting, ice cube melting in water, that was a while ago. Okay, if this is going to be true, here's a neat way that, like, if you go into grad school in PChem and you end up like in a theory group, the way you explore thermodynamics is, for this to be equal, well, they have to be equal. So what you could do is perturb it by adding in a change. Perturb it by changing it, but so small that you're not changing it, right? Add in a partial. So you're changing it, but not really. That's kind of clever. Okay, so what that means is that the other part has to change too by the same amount, or they're not equal. So if 5 is equal to 5, then 5 plus delta is equal to 5 plus delta. That's the idea. So I mean, it's again, it's kind of childlike, simple, but there you go. So the chemical potentials, and so are the changes of chemical potentials. Those are equal. All right, now change in chemical potential, as you were hopefully sick to death of, dF is dF dx, dx, dF dy, dy, right? So we're going to play that game again. And I am going to bore you to death. I'm going to do, there's actually a very easy way to do this, but I'm going to do it the slow way, just because. Now I'm going to have temperature and pressure as my variables. And remember, chemical potential is going to be in the G representation. Remember, chemical potential could be anything I want it to be. Enthalpy, internal energy, Helmholtz energy, or Gibbs energy. But I'm going to make it Gibbs energy. And that'll come up in 1 second. And of course, P and T are my deals, so I'm going to expand them in terms of pressure and temperature. All right, now this is where this gets kind of neat. And I got to remember that chemical potential. So I am doing this in a much more complicated way than I need to. but I'm actually doing it this way. I don't really need to do it this way. I actually just kind of want to remind you on how to manipulate partials because we haven't really done any of this in a while. All right, so, I'm working with this, and I'm going to work in the constant temperature and pressure regime, and that means chemical potential is the change in G. And the change in G, God, I'm using the board like a game of Tetris. But anyway, minus SDT plus VDP. All right. So now what? Let's see. Okay. What I have to do is I have to get these guys. I'll do this one first, right? Because you know that this is going to be, well, it's going to be minus entropy. You can kind of figure that out. Well, actually, not quite. And here to show that. And again, I'm just really going out of my way to do this like exactly perfectly, because you know if this was truly a full-blown math class, it just reminds me of those geometry proofs I had in sophomore year of high school. Okay, TP does matter what you hold constant. T. Okay, there we go. Okay. Weird symbology. Okay, so this is the kind of thing maybe I'll put this on the partial credit of exam third, maybe even the final. Not this, but something like this. Gibbs Energy is exact, and that means I can play this trick. I can switch the order of differentiation. And that's a constant P, constant G. I can switch the order of differentiation. Now the reason I just did that is dg dt at constant t and p. No, wait a minute. Wait, I can't. Oh, no. Yeah. dg dt at constant p is right there. It's minus s. Okay, so this is the change in n, and that's minus s. Really not much to it. I'm going out of my way, and you should know that this ends up being S over N, which is minus S per mole. And the way I do that, it's kind of, there's two ways. Let me just make it sensible to you as though you're in middle school. The amount of craziness, if I add a cat, how much crazier does it get? Well, if I have 5 cats and it's 5 crazy, one more cat makes it one more crazy, right? Another way to do it, which is not so ridiculous, is to note that you can basically, you've seen me do this a couple times, you can integrate. You can integrate things that are extensive. You can integrate things that are not extensive. It's just that it's a little bit different when they're extensive because your lower limit can be 0. So, and what that means is that I've got what am I describing? A bucket of ice. I can have an empty bucket, and there would be no moles and no entropy. If I filled the bucket, there would be a mole and however much entropy. Anyway, it's all sensible, but I just also want to point out to you that there is a rigorous mathematical reason that I'm not just doing this kind of willy-nilly because it seems right. Okay, likewise, the change in chemical potential with respect to pressure, at constant temperature, and I'm just going to write down the answer because it should be really quite obvious. Maybe this is what I'll put on the test. What have I done? 2p constant t, and that'll be change in v, change in n. That'll be a constant t, and that'll be volume per mole. So now the reason that, again, I've done this like, this is like perfect. This is like God's truth. God's a mathematician. The reason I didn't really have to do this is that basically I could have taken this expression for delta G and I could have divided the whole thing by n. And that would have been fine too. It would have been the same thing. Okay, with that said, let me write out the whole thing. Actually, wait, before I get there, I'm gonna leave this up here. I know that I'm not using the board super well today, and again, I'm a game of Tetris. But I'm going to show you something that's kind of instructive for why does the P versus T phase diagram change the way it does. And these are drawn in the book as well. And I think they were drawn a little bit better than I can put it today. But what I want to do is write out the chemical potential as a function of temperature. And what I want to do here is, again, I'm slowly but surely trying to justify how these lines look in the phase diagram and how I come up with an equation to describe said lines. Okay, and I'm starting out with the middle school level. I'm trying to make this make sense, and then we're going to be mathematicians. Okay, now at low temperature, let's do solid liquid. Let's do solid liquid. What has a lower chemical potential if you're super cold? The solid or the liquid? Oh, the solid.
You want to be lower. You want to be lower.
Low temperature, what's present, solid or liquid? Which has a lower chemical potential?
Solid.
There you go. Okay, now I'm going to increase this with temperature. I'm going to figure out how the chemical potential changes with temperature. I'll just draw a line. I'm sure it's not really a line, but I'm just going to draw it that way. Should the line point up or down?
Down.
There you go, right. So the line points down. And it won't point down too much because solids have don't have a lot of entropy. All right, that makes sense. In fact, if I'm low enough, it doesn't have any entropy. Okay, now the liquid is higher. The liquid's going to start out higher at a lower temperature, higher chemical potential because there's no liquid, but it has a greater entropy. Right there. All right, so guess what? There you go, liquid. And this is, of course, that's our, I'll be exact, that's the fusion temperature, right? The melting temperature. I have to call it fusion. It's weird, but whatever. Okay, now I play this game further, and I know that a gas has a higher chemical potential than a liquid at low temperature. Actually, that's a bit of a guess, but I think it's a good guess. But a gas has a ton of entropy. So that's gonna come down real hard, real quick. And there we go. And now I see the vaporization temperature. There you go. All right, so not much to this. Now in your homework, I throw CO2 at you and I play some games because CO2 actually goes from solid to gas without going through the liquid at 1 bar of pressure. At other pressures, that's not necessarily true, but anyway. So I have you look at a little diagram like this and try to arrange it like little sticks, and you'll figure it out. It's kind of clever, but it's kind of easy too. All right, so there you go. Not much else to say about this, but now I wanted to talk about a little bit about now pressure, because if I'm going to do a phase diagram, I have to include pressure. And there's not much to say about that, except that water does something weird. And normally, I mean, everything, if you look hard enough, there's something weird everywhere, but water's kind of important. So let me call this not water. Okay, everything else, but not water, and then I'll do water, because this will make more sense to you. And what I'm going to do is I'm going to add the effect of pressure. Okay, so I'm going to do solids and liquids. So what I want to do, I've got to remind myself, okay, I'm going to draw a line for the solid. Okay, the gas and the liquid's the liquid. But if I pressurize it, I'm going to draw another line. You see that the problem, what's funky about this is I need to include pressure, but pressure isn't an axis. So this is a little funky, right? Actually, in the book, you may have noticed that the way I did it was I tried my best to draw a three-dimensional picture with the computer. But anyway, for this class with this board, I have to include pressure, but it's not an axis. What should I do?
Draw another line.
Yeah, draw another line, right? Would it be above or below this line?
Above.
Right, because volume, right, Gibbs energy increases with volume. Okay, so I'm going to increase pressure, and I'm going to do it this way. And I'll just do 3. Okay, so now the way to do the liquid is here. I'm going to draw a line downward. Okay, and that's the liquid. But a liquid, if you're not water, if you're a liquid, liquids tend to expand. Right? So liquids expand, and that means that they're more sensitive to pressure. Their Gibbs energy increases, Gibbs energy per mole increases more than the solid. Most liquids occupy more volume than most solids. So if water, which is weird. Okay, in that case, what we've got is a situation like this. Now again, I haven't really labeled it on this graph so well, but hopefully you know what I'm doing. Okay. Now, what's the point of that? Is that what I've given myself are some points. I've given myself 3 points. See, I can see what I'm doing? I can start mapping out the pressure, temperature, phase diagram. I'll start with the triple point. Again, I'll always have some knowledge of the triple point. You just can't not know nothing. I mean, it's what chemical am I talking about? Well, don't you know? No. So let's see here. What's happening? Okay, these crossings are the equilibrium points. And let's see. As I increase pressure, the equilibrium point occurs at higher temperature. Okay, so again, let me say that again. If I increase the pressure, so I need to go up, the temperature likewise increases. Okay, so what's dP dt? Positive. Right, positive, so there we go. So I've got myself 1, 2, 3. There we go. Solid. And just to calibrate you, now I'm not going to bother with all this, but there's our gas. So anyway, just so it adds up to you. Okay, next one. Now let's do water. I'm going to do the same thing. This is really hard to draw, so not. That's like the third time I've written that down. I just need to give myself a little bit more room. I'm not sure what I need to do. Okay, I got to get my little graph here. Okay, so I swear this is a nightmare to draw this right. Okay, I got to do the solid, and the solid is weird because its volume per mole is greater, right? Volume per, wait a minute, what have I done? Yeah, the volume per mole is the density is less. Wait. So I've got myself confused. That's 1 over, this is 1 over the density, right? Yes. Okay, so if the density of the solid is less, then this is greater. Right? Yes, okay. All right. Oh my God, this is easy, but it's not. Okay. If this is greater than for the solid, then I need to draw the line spacings actually really quite wide. Now, I'm not going to label it. I'm just going to assume that you know what I'm doing. Okay, and now the liquids don't change so much. Let's see here. How do I want to do this? You know what? No, that doesn't work. See, I told you this is a nightmare. I've got to just line the ducks up just right. And again, look, I'm kind of drawing this arbitrarily anyway. And the thing is, the lines have to be over each other. And so sorry, I know I'm a little flummoxed here. Okay, so that would be the liquid crossing. Now, there's the next one. And the next one is right there. Okay, that came out crappily, but anyway. Here's the temperature. Here's the temperature. Here's the temperature. Sorry, this did not go so well. It never does. I struggle with this every time. Okay. P versus T. If the pressure rises, the temperature goes which way?
Up.
Right. Up. It went up.
Yes.
Low pressure, high pressure, temperature went down. Right, temperature went down. Okay, so that means if I go up in pressure, do I do this?
Nope.
No, I do this. Huh?
Yep.
Yeah. There we go. And again, just to calibrate you, let's just say that we have this information as well. Okay, so there you go. Again, sorry for my, I can draw okay, just not, I need to practice a bit more. All right, so anyway, just one way for you graphical folks to understand why these look the way they look. Now we're going to derive equations for the lines. I do want to point out one thing at this point, because I'm not going to do anything more with these. You see that I have a question on the homework on this. I usually have one on the exam too, and again, I'll think of something clever. CO2 or maybe naphthalene. Naphthalene also behaves like CO2, it just sublimes. There's one thing that's kind of funky that for those of you who did stick around the next hour, and again, I will post that video, and you've actually, maybe you've looked at the book, but when I do this, when I did it yesterday, Friday, and in the book, when I try to draw phase diagrams by mapping out chemical potential versus temperature and pressure, with temperature, my chemical potentials actually went up, not down, with temperature. Do you guys remember that? Did you notice? Maybe you didn't notice, but yesterday, Monday, I actually did do my tags. When I was talking about mapping out chemical potentials and making and equilibrating things and adding salt on Friday, maybe you didn't notice, but at higher temperature, my chemical potentials did not drop, they actually went up. It's also in, there's a fancy picture in chapter 8 where I draw a phase diagram and I do it with chemical potentials. And again, they actually rise with temperature, they don't decrease. But that's counter to what I just did here. Any idea why that discrepancy exists? Huh?
Is it constant motion?
Were you here Friday? You were here at the next hour. What did I call chemical potential? Remember, if I actually have to start putting numbers in the calculator, what did I use?
Oh, I was going to say the mu is basically like G over M.
It actually, well, hold on. G over M? Actually, no. It's actually not what I did. Now again, folks, this is all nice and hypothetical, but calculator, boots to ground, I don't actually do it this way. How do I do it? What's my chemical potential when I actually need to get real numbers? It's not the G, because I don't know the G. What is it?
RT of X.
No, but you're thinking in the right direction. You're still saying a calculator. But what do I inherently call chemical potential when I need to get actual numbers? No.
Work.
Wait, folks. Delta formation G per mole. Right? Now, what I've done here, let me erase, don't write that down, don't write that down, because that's not what I've drawn here. So remember, this is all fine and good, and it's all correct, but when I need to actually put numbers in a calculator, I don't really know what this is. Remember that this is technically, now you can't put this down, this is the Gibbs energy per mole, but I don't ever truly know the Gibbs energy per mole or Gibbs energy of chemicals because I have no reference point. If I kind of make up a reference point, that being chemicals in their elements in their standard state, and I start using delta formation G's per mole, this stops working. The concept is fine, but it doesn't quite work this way. And in fact, again, chemical potentials as defined by delta formation G's, in the examples I gave on Friday and in the book, those actually rise. And that's because what's happening is, it's not the chemical water, it's the chemical water minus its precursors, hydrogen and oxygen. So that's why there's a discrepancy. There's the question. Okay? Alrighty, anyway, any questions before I move on, because we're almost done with this. Alright, so anyway, I just wanted to point that out, and again, it's a subtlety, but if you are paying attention to that stuff, you may be like, hey, wait a minute, this isn't what was done in class, and that's why. And I'm not sure how to resolve that. As I mentioned to you, with computers and quantum mechanics, we actually are able to get to the absolute internal energy, and from there we can build Gibbs energy. We are able to do that now, it's just that it's not, we can only do like 10 atoms at once into a supercomputer to get accurate numbers, so that's not so great, but we're getting there. So maybe one day, maybe 100 years from now, we'll wipe out all the data tables and put in absolute Gibbs energy, and that would actually make things a lot easier if we did that. And we're kind of moving towards that. All right, anyway. Let's just, so I'm starting, to make sure that you know what the heck, I'm like going in a different direction, so that's a little wiggly line. Different direction. Now I'm going to mathematically describe the lines, and again, fodder for simple questions that are on your homework and on the exam, and free points. Look out for the derivations, that'll get you. Okay, I'm going to still start with the change in the chemical potential. Again, the chemical potentials have to equal, if I poke them with the lightest touch, like a little needle, you got that right. You got that right. Anyway, if I poke them with the lightest needle possible, then the perturbation is very small. That's fine as long as the liquid and the solid match, right? So this way the chemical potentials remain in equilibrium. Okay, now I'm going to take it for granted that you know that we're going to work in a constant temperature pressure world, because that's how I drew the phase diagram. And so what I'm going to have to do, this is where it gets a little tricky, is I have to make sure that I keep the phases, make sure I know what phase is what. Okay, and then I have to do the same thing for the beta phase. And again, the challenge here is not getting confused between the alphas and the betas. When I was writing the book, I had to look at this like 10 times because I kept doing alpha and beta switch just as I was writing it out. But anyway, so look out for that. Again, this looks like good fodder for derivations on the next test, which is coming up. Okay, now what I do is, it's pretty simple. I'm going to keep alpha here, and I'll bring over beta. And that allows me to factor the P. And let's see here, now what have I got? I can bring over, so it's just a now you see why I get a little bit flummoxed, because you have to keep it straight, what subtracts what. Okay, anyway, I just did some factoring. And then what that allows me to do is figure out dP dt, which is, I'll write it out just so you don't get confused in your notes. Notice also what I like about this is, remember, entropy is defined. Nice thing about the third law. No third law for internal energy, but there is one for entropy. So this isn't a delta formation entropy. That's a pain in the rear. It's entropy, and I know what the entropy is. And plus I've got alpha minus beta for both. And that certainly makes it just a little bit easier. And so I can subtract the entropies and the inverse densities. Remember, that's the inverse density. You saw that kind of got me upset there a second ago. Okay, now, just for the heck of it, although we do have entropies available to us, let me do a short little derivation. It's kind of, there's nothing wrong with working with this, although I can kind of simplify it, and it reconnects to what you are used to, maybe in high school and whatnot. Let me write dH. What I don't like, as much as I have no problem with entropy, but there's a way to simplify entropy, which is, and I want to do this mostly just so that you're not forgetting this stuff, because God knows. Oh, on the next homework, by the way, I'm going to have some questions from like chapter 1 and 2, just to force you. I'm going to force you to study. People hate it when I do that. But okay, so I'm going to want to do this at constant temperature and pressure. And so the T is constant and the pressure is constant. Oh, but that wipes that out. And that means that ds is dH over T. Okay, now oh, here, let me, that's a nice derivation, but I really did it just to remind you how to do this. The second thing is in a constant pressure world, enthalpy is heat. Heat over temperature is entropy. So yeah, okay, it makes sense two different ways. Okay, and then I can integrate that, I won't bother. Delta H per mole over T delta V. There you go. And this is called, well, let's see, I cannot pronounce this. What the hell? This has a name, and I didn't write it down. Clausius. I am doing that off the top of my head. I have no idea if that's actually correct. Clausius-Clapeyron, whoever the hell that is. I'm glad he's dead. Anyway, okay. So with this we're almost done. As you can imagine, now what I'm going to do is I'm going to have dp on the left, and I'm going to bring t over to the right and integrate. And with the triple point as a lower limit, and the upper limit being the P and T that I'm looking for, P and T. So I'm trying to build is P and T pairs. I have 1 degree of freedom. I'm describing an equilibrium between solid and liquid, or solid and gas, or liquid and gas. So I have 2 phases present. That means I have 1 degree of freedom. That means I'm drawing lines. And if I'm drawing a line, then my change in y is what I'm looking for, given a change in x. And then I can make x, y pairs or pt pairs and draw the phase diagram. Anyway, that's the idea. Okay, so I'm just going to do 2. I'll do solid liquid. And that's because you're going to see why, mathematically why, water slopes one way and ethanol does the other, ethanol and everything else. And then I'm going to do solid, what do I do? I'll do vapor liquid and vapor solid sublimation, that's the same thing. Okay, there's not much to this. So what I'm going to do is I'm going to bring dp over, and let's see, that's fusion, right? Yeah, liquid, yeah, that's fusion. H per mole, and you can look those up, and you know that of course there's an approximation here. If you use, if you're looking at, let's say that this is water. Let's say that I'm asking you to create the water line. Fusion enthalpy is temperature dependent, so we're just going to make it a constant when I do this integration, but that's like a major approximation. So a little bit of stupidity here. Now the main thing is is defining the limits. And so the lower limit, we will make it the triple point. And again, I've said this the whole time we've been bringing this up. I can't do anything with this phase diagram stuff unless you give me a little information, like what's the triple point. I have to have something. Okay, the upper limit is the TP pair. In other words, give me, we're going to solve this for a T and a P. And that's a point, and then I draw that point on the phase diagram, and then I just repeat with different P's and T's, and I can create the line that way from a bunch of points, just like you saw me do before. Like taking discrete P and T points, and I can draw the line between them. That's the idea. Okay, there's not much to this. I got P2 minus P, let's call it the triple point, is equal, actually, you know what, I'll bring that over to the right, so I'm going to go ahead and do a little algebra. And this will be the fusion enthalpy per mole over the change in fusion volume per mole. And of course, an integral of 1 over x is natural log. There we go. Not much to it. The neat thing is, though, that I can see some behavior in here. Again, assuming that I know the triple point. And what is this, solid liquid? Okay, this actually looks like a line, because this is y is mx plus b. this is something that comes up, I brought this up a few times. Natural log of x is kind of just like x. Natural logs take a line and they just kind of bend it over a bit. Natural logs are kind of linear. So this looks like a line. With the slope, what do you think of that slope? Is that big or little? Now, this could be large, and it usually does take a lot of heat to melt things. But what about this factor? Really small. Solids tend to be more dense than liquids, but not by much. Right, so this is a tiny number. So what I see here is that this is like a line with a real hard slope. Just like I've been drawing it the whole time. Now, why does water slope the wrong way?
Because it's less dense than the solid phase.
Well, where's my minus? I need a minus sign, right? It slopes this is a positive slope, water has a negative slope. Where's my minus?
From the natural log.
Okay, natural log of a number greater than 1 is positive.
The volume.
Volume. Change in volume. Fusion is the process of melting. That means that this is the volume of the liquid minus the solid. The liquid volume is what? Greater? Less. Yeah, less, right?
Smaller.
I'm confused. It's negative. It's negative. That's why. What? Right. Water does this. There we go. Okay, solid, and again, we'll just assume that we have the rest of it. Gas. Okay. So there you go. Okay, last one, and we're done. So I'll actually end on time, which is a record for me. Is I'll do liquid vapor, and solid vapor, which is a thing, is the same. Just use sublimation. Okay, this gets kind of neat. This is kind of neat. Let me just put my starting point up here. T delta. Okay, here's what I want to point out. Okay, the change in vaporization volume. Vaporization is a liquid turning to a gas. That means that this is the volume per mole of the gas minus the volume per mole of the liquid. Now, you got to be careful with that because if you get confused, this is why the symbology really does matter, and it really does matter what IUPAC, International Union of Pure and Applied Chemistry, it really matters how they define things because otherwise you're going to pick up a minus sign somewhere. That's going to mess things up badly. You'll lose a point if you do that. Okay, now, guess what approximation I can make here? I'm going to make an approximation. You guess what that might be?
That the volume per mole of the gas is basically the same as that minus that, because the liquid is such small.
Right. So the change in volume is just the gas volume. Right. That's exactly right. So, and then of course this is we'll use a perfect gas law, and I'm blanking out RT over P. Okay, so this ends up being, and I'll bring over the dt at this point. And now what I've got is I've got a t squared. So don't forget I'm actually flipping this. And now I've got an r here as well. And now I've got a change in p, but I'm going to bring over the p. So as you can see, I've actually kind of messed this up. I've actually changed a bunch of stuff at once. Let me see if I actually did that right. Yeah. Okay. All right, now you integrate it. And just assume that the limits are the same. Again, I have to give you the triple point, and then there'll be an upper and lower, the two different upper limits. That's the things we're looking for. And what you end up with is Lm of the pressure over the pressure at the triple point. Again, given to you. I have to give it to you. Just like I have to give you the, let's see, I'm going to pick up a minus sign here, right? Yeah, you don't pick up a natural log. But now I've got t squared, so I'm going to pick up a minus sign. Let me make that a little bit, better. and then we just simply got 1 over T2 minus 1 over the triple point. Okay, so now the way that this would work, this little game would work, pretty much done here. Now imagine I'll give you the triple point pressure, the triple point temperature, and the way you would do this is you would say, okay, the triple point of water is around, it's like 270 K. It's right below, it's slightly below 0. Is where the triple point temperature is. And what you would do is you plug in more and more temperature, 300, 350, 400, on and on and on. And then that gives you a corresponding pressure. And you would you draw the line that way. It's like Y versus X. In fact, there's a couple things to note here. On the homework, if you simplify this, I want to point out something real quick. You can simplify this to this form. Natural log of pressure is basically a number minus a different number over temperature. So this is what this collapses into. And the way, and so I ask you questions on, this is the last homework question. What you want to do is figure out how to turn this into a form of a bunch of numbers and leave that temperature, by the way, that's right here. That's that temperature. So you can see that the constant here, that is actually minus the enthalpy over R over the triple point temperature. That's this number. And anyway, the last thing I want to point out is that this, let me bring this to the e'th power. Pressure looks like e to a function of 1 over temperature. It basically looks like an exponential rise. So in a P versus T diagram, here I'll do water. Starting with the triple point, what did I do? Liquid vapor. The liquid vapor pressure versus temperature is basically a exponential rise, just like I've drawn it. Just also like solid gas. Solid gas is also an exponential rise, just like that. Okay, anyway. All right, folks, that's it for chapter 8. That's actually it for the book. I don't know what we're going to do here. It's also